Everybody. So we've kind of hit the first set of videos got us to a really big point, right? We were examining, just draw a quick graph. We've got some function, I'll call f of x, and we're interested in knowing the slope of what we call the tangent line. That's terrible. Let's do that again. Closer. So we want the slope of the tangent line, right? Which we know is equivalent to thinking of the instantaneous rate of change. And the way we get it is we can take points nearby and make approximating secant lines, right? So a couple on each side, one on each side, right? But then we imagine sliding those points together, and we came up with the definition of the derivative. If we've got a function y equals f of x, we call it y prime or f prime of x, and we take this limit as h goes to 0 of f of x plus h minus f of x all over h, right? This is, we can think of this point here as x, f of x, and then any of these approximating points as being the points x plus h, f of x plus h. And so this limit is our algebraic way of writing down this geometric concept of sliding those points closer together so that the h goes to 0 is that difference becoming negligible, and we see what the tangent line slope is, okay? This definition is great, it's genius, and the people who figured this out are amazing, but it is also cumbersome and can become tedious at times or unbelievably complicated at times, right? It's not always easy to figure out. A lot of the examples we've done and problems we've worked through are the ones that we can actually do or can actually do in a reasonable amount of time. And other ones become really, really unwieldy really quickly. And then some of them, we're doing the same things over and over again, and we might start to recognize patterns. So what we're going to do now is we're going to take this idea and we're going to develop differentiation rules. Okay. What we're doing is we're not leaving this definition behind. This is always what the derivative is, okay? And this picture is what we always want to have in our heads, as well as the concept of instantaneous rate of change, right? These are all still important, okay? But it's going to become easy to lose sight of these, because what we're going to do is notice that if we do this to certain kinds of functions, patterns emerge, and we might as well skip over doing all of the algebra each time, right? It's like if you learn to do a plus b squared, when you learn it, you go, okay, a plus b times a plus b, and then you say, well, I gotta multiply this first thing, this whole parentheses, I can distribute it, multiply it by a, multiply it by b, and I get a plus b times a plus a plus b times b, and then I'm going to distribute this thing to both of these, and I get a squared plus ab, and then I'm going to distribute this thing into these parentheses, and I get ab, oops, forgot my plus, I get plus ab plus ab plus b squared, and then I notice I've got two of the same thing, so I can combine them, right? Well, we don't need to redo this work every time, right? And so after you've done something like this 100 times, you just jump to the end, right? But it's still all of these rules we use, the distributive property that we used, and then collecting like terms, all that stuff still is what's happening. We just don't need to see it every time. But we need to understand that's what's happening, so when things get complicated, we don't, we have a way to do it. We still understand the fundamental rules. And that's going to be the case with derivatives. We're going to develop some rules that let us shortcut this limit definition, but we don't want to lose sight of that, which is why I'm going to bring it up repeatedly in every video. Okay, so with way too long of a preamble, let's get into the rules. The first rule is pretty straightforward. The constant rule, and actually this first set of rules are all pretty straightforward. The constant rule For constant functions, let's say, let's let C be a real number. So remember, this little set of symbols just means C is in the set of real numbers, right? It's a constant. Then if f of x equals C, right? This is the constant function. F prime is going to be equal to 0. Okay, so let's first intuitively figure out why this is, or geometrically maybe. If I graph a constant function, here's my x-axis. I guess I'll draw on a y-axis, right? A constant function is flat, right? For every input, the output is the same, right? Well, what's the rate of change? Remember what the rate of change means. It's how does the output change as we change the input? This output doesn't change as we change the input. So the rate of change is, of course, 0. Okay. We can also prove it with our limit definition. Let me write this one other way. We can also, just to keep using other notation, the derivative ddx of a constant is 0, right? Saying the same thing without having to name a function. So how can we prove it? Well, let's assume f of x is equal to C, where C is a constant. Then f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, what is f of x plus h? Well, we know one thing about this function. It spits out the same number each time. F of x plus h is going to be C. F of x is also going to be C. C over C is 0. So we get 0 over h, which is just 0. 0, the limit of a constant is that constant. So this limit is 0. And so we get that f prime of x is equal to 0. So we don't need to do this anymore. Anytime now that we see a function that's a constant and we want the derivative of that function, we know it's 0. We don't have to do these steps, right? You can see if I took the derivative of the function f of x equals 5 and did this limit definition, I'd have 5 minus 5. If I had the function f of x equals 105, I would have 105 minus 105 in the numerator would disappear and we get 0. So we don't need to keep doing that work, right? So if f of x is equal to 7, then f prime is equal to 0. If g of x is equal to pi, then g prime of x is equal to 0, right? So we can do this forever. They're always going to be 0. Okay. All right. Great. Let's add another rule. This is one we've probably, maybe some of us have noticed already. We've done a few of these derivatives. So I'm going to write the rule first. No. Let's start with a couple of examples. We've probably seen these before. We've probably done this one in a previous video. If f of x is equal to x squared, f prime of x is equal to the limit as h goes to 0 of x plus h squared. So this is f of x plus h minus f of x, over h. We'll get the limit as h goes to 0. So now we've got our x squared plus 2xh plus h squared minus x squared all over h. The x squareds are canceled. We have the limit as h goes to 0. So the x squareds are canceled. We can also cancel a factor of h in the numerator, right? Because there's an h here and an h here. So we factor those out. And all we're left with is 2x plus h. Now the h goes to 0 and we're left with 2x. So f prime of x is equal to 2x. Let's write this one. F of x equals x squared and f prime of x equals 2x. Let's do a similar thing for x cubed. Okay. So f prime of x will be the limit as h goes to 0 of x plus h cubed minus x cubed over h. This is going to be the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed, right? So those first 4 terms are from that cubed quantity, and then the minus x cubed is there. So we lose these again. And again, we can factor out a factor of h in the numerator and cancel it with the one in the denominator. So each term here is going to lose a factor of h. So we'll end up with 3x squared plus 3xh plus h squared. All the h terms go to 0, and we're left with 3x squared. All right. So this is our f prime of x. So we have now this observation that if f of x is equal to x cubed, its derivative is 3x squared. Okay, so there's a little pattern that's happened here. Notice this exponent ended up here. The exponent of 2 ended up in front. And the exponent on x, we don't usually write it, but there's a 1 there, has now gone down by 1. The same thing has happened here. The exponent 3 has gone to the front, and the exponent left on x has gone down by 1. And it turns out that this pattern continues, okay? So right now, we only have enough to prove it when n is a positive integer. I'll spoil the ending. It turns out that this is going to be real for all numbers. But for now, let's show that it's true when n is a positive integer. So if this is our power rule for derivatives, if n is a positive integer, and f of x equals x to the n, then f prime of x is equal to n times x to the n minus 1. Okay, the exponent comes down front. The one in the numerator becomes lowers by one number. Okay, so the proof of this, I'm not going to do it in detail. It uses a few not horrible things, but I'll probably make a separate proof of it for everyone to see. But I can summarize it this way. If we've got f of x equals x to the n, then f prime of x is going to be the limit as h goes to 0. We're going to get x plus h to the n minus x to the n over h. All right. So this first term here, the x plus h, my n's and h's are looking very similar. The x plus h to the n is going to look like this. It's going to have x to the n plus x to the n minus 1, sorry, n, pardon me, n times x to the n minus 1 times h, plus, and so what we're using here is something called the binomial theorem. We know what all of these coefficients and how the terms are going to be distributed, but all that matters is this: everything that comes next is going to have some kind of constant, and the powers of x are going to go down, and the powers of h are going to go up. Right? Then there'll be an x to the n minus 3 h cubed until we get down to something like nx h to the n minus 1 plus h to the n. And then we have this minus x to the n. Okay, so the part I'm hand waving is all this stuff in here. All that's important about all these terms is that they're all going to be a constant times a power of x that's getting smaller, and powers of h that are all at least h squared. Okay, now what's going to happen? X to the n's are going to cancel. We're going to cancel. We're going to use this h in the denominator and factor out an h in the numerator. This h is going to cancel completely, and we're going to be left with nx to the n minus 1 plus everything left in this parentheses has at least one power of h left on it, right? Look what happened up here when we canceled. We had an h squared, h cubed, right? We canceled one factor of h. We factored out h, and what was left, the first term had no more h's left, but the one that was h squared became h, the one that was h cubed became h squared, and when we took the limit, those things with h's attached to them became zeros, right? The same thing happened here. We had a 2xh plus h squared. When we factored out a factor of h, the one that only had one h multiplied had none left. The one that was h squared became h. So all of the terms that I'm representing with these two squiggly lines have at least one factor of h attached to them, which means when we take the limit as h goes to 0, they all disappear, and all that's left is nx to the n minus 1. Okay, so all this hand wavy in there is part of the binomial theorem, which just tells us how these things, when we have an a plus b to some power, how does that work out in the end, right? It's really just an extension of what I did up here. This is the case where n equals 2, and you may have seen before, if you have a plus b cubed, you get a cubed plus 3a squared b plus 3ab squared plus b cubed, right? That there's a formula that lets us represent what happens when it's a 4 and a 5 and a 6 in the exponent, and on and on and on. But in all cases, you end up with the first thing to the power that you took it to, the second thing with a coefficient, one less power than the original exponent, and the other thing you have one factor of, right? That other thing for us is our h, and so we always end up with this first term ends up getting canceled by the subtraction. This term we lose the h when we factor it out, and the rest of them have higher powers of that h, right? So I've already spent more time on that than I wanted to. This is the formula we end up with, right? This power rule for derivatives. This is great because, as you saw when I took these two limits of x squared and x cubed, right? You have to expand these things, and even by x cubed, it's already getting pretty tedious. And so if I had something like f of x equals x to the 7th, right? If I tried to do the derivative with the definition, the first thing I'm going to need to do is expand this, right? And expanding that is going to be ugly. It's going to be a really, really, really ugly thing with lots of terms. And the notion, the idea that we might get through that without making a careless error seems like the odds of doing that without a careless error are pretty slim, or we're going to take an incredibly long amount of time. But with this power rule, I don't need to do all that. I know exactly what's going to happen when I do this limit. The power is going to come down front as a constant, and the new exponent is going to be one less, 7x to the 6th, right? So this is pretty fantastic, right? So it doesn't matter how big this exponent gets. If it's a positive integer like x to the 103rd, we get 103 x to the 102, right? And we would not have to spend our time expanding this x plus h to the 103rd power, which would be an immense time commitment to pull out. Okay, so this is great. We've got constant functions and we've got power functions, right? You might feel like, well, we're getting close to polynomials, and we really, really are. We need a couple things and we'll be able to do polynomials. So let's do those. Let's add two more rules, and then we'll see that we can end this video where we've got polynomials under our belt. Here's the two rules we need, and these are both pretty easy to show. So we're going to have the sum and difference rule for derivatives. And this just tells us that if f of x and g of x are differentiable functions, they have derivatives, then the derivative of their sum or difference is just equal to the sum or difference of their derivatives. Okay, which we could also just write as f prime of x plus g prime of x. Okay, so if you have two functions whose derivatives you know, and you add them together to create a new function, when you take a derivative of them, it's just going to be the sum of those two derivatives. Right? So intuitively, let's think about instantaneous rate of change. If f of x is changing at some moment by 2, I'm just going to say y's per x, right? Maybe it's miles per hour. Let's say that. If f of x is changing by 2 miles per hour and g of x is changing by 10 miles per hour, and you're adding those speeds together, right? Maybe these are the speeds caused by some force, and you put these by some engine, and you put both of them on something, so it now gets the force of both of them. You add these speeds together, you're going to get 2 miles per hour plus 10 miles per hour. You're going to be adding 12 miles per hour. That's it, 12 miles per hour, right? So let's prove this one. This is pretty straightforward. Let's let f of x and g be differentiable functions. And define L of x to be, I'm going to do it for sums just to keep this notation simple, but you can do everything I'm doing with a difference here. So let L of x be the sum of these two. Let's bring this over here so we can have some space. Then L prime of x is equal to the limit as h goes to 0 of L of x plus h minus L of x over h. That's just our definition. Sorry, I see that I'm going to need a little more space. So let's being sloppy. Okay. All right, here we go. So now, well, what is L of x plus h? Well, the definition of L is that it's the sum of f and g. So this just means f of x plus h plus g of x plus h. Then we've got minus f of x plus g of x all over h. All right. So now let's just do a little bit of algebra. I can rewrite this as f of x plus h minus f of x plus g of x plus h minus g of x, right? So I distributed that negative to both terms, and then I did a little rearranging. Now I'm going to think of, in my head, these two groupings and rewrite this as the limit as h goes to 0 of f of x plus h minus f of x over h plus g of x plus h minus g of x over h, right? So that's just how fractions work. Now I'm going to use my limit laws. The limit, when we have the limit of two functions that are added together. So I'm thinking of this whole quotient as one function and this as another one. My limit laws let me distribute the limit across these two. So I've got f of x plus h minus f of x over h plus the limit as h goes to 0 of g of x plus h minus g of x over h. F and g are differentiable functions. What are these two things here? These are their derivatives. This first one, this is the definition of f prime of x. The second one is the derivative of g prime of x. So this function, which is defined to be the sum of the f and g, its derivative is just the sum of those derivatives, right? This is great. So now once we have a derivative for a function, a couple of functions, if we put them together, there's nothing complicated that needs to happen. We can just add those two derivatives together, okay? And then if we change this plus to a minus, everything in here works out the same. I'll leave that as an exercise for you, but it all works out so you can pull the same maneuver to get this result. Okay, so for example, if I have, let's take the derivative, well, let's take f of x equals 7 and g of x equals, x to the 5th. Then if I want to take the derivative of f of x plus g of x, well, let's just write down these two derivatives. We know from the constant rule that we developed first that the derivative of a constant is 0. And we know that the derivative, we can use our power rule for this x to the 5th. We get 5 coming down, x to the 4th. And we know that this derivative is just adding those together. So we get 0 plus 5x to the 4th. In other words, let's write this another way, d dx of 7 plus x to the 5th is equal to 5x to the 4th. Okay, so no, we'll do a couple of big examples at the end with all of these rules combined. So let's do, we're really close now to polynomials, right? The only thing is polynomials don't just have power functions like x to the 5th, x to the 10th, x to the 100th. They have constants in front. So the last rule we need is what happens when we have a constant in front of our functions. So this rule will be the constant, let's just call it the constant multiplication rule for derivatives. Okay, so let's have, let's let f of x be differentiable and c is a real number. Then the derivative of this constant if we take this constant and multiply it by the function, right? You can take a function, multiply it by a constant to get a new function. And we want to take the derivative of that. It turns out that this constant, when multiplied by a function, can slip out past the derivative, right? And we end up with that constant times the derivative. Okay. So again, intuitively, let's use slope of the tangent line for this one. If I have a function f of x, let's do this. And I know the slope of its tangent line right here. So remember, the derivative gives us the slope of this tangent line. If I multiply f by a constant, let's make it a positive constant in our head for this drawing. Like, let's say I multiply it by 2. I know that each value of my function doubles. And this new function gets stretched upward, right, vertically. The tangent line at the same point is going to be steeper, right? How much steeper is how much did I multiply it by? Right? Think about lines. If I take a line, the function that's a line with a slope of 2, and I multiply that function by 3, its new slope is 6. Okay, so that's one way to think about what's happening here. But let's prove it. This is an easy enough one to prove. So if we have, let c be constant and f of x differentiable, let's define L of x to be a new function made by multiplying f, the function f by the constant c. Then L prime of x is going to be the limit as h goes to 0, L of x plus h minus L of x over h, which is the limit as h goes to 0. So L of x plus h is just c times f of x plus h. L of x is just c times f of x, right? This is just our definition of L, all over h. We get the limit as h goes to 0. I'm going to factor c out. We get f of x plus h minus f of x over h. Whoops, that was just supposed to be in the numerator. Now, we have a constant times a function, right? C times this thing. We have a limit law that tells us that those constants can slip out in front of the limit. And so we're left with f of x plus h minus f of x over h. And then, of course, what is this thing I'm staring at? The limit of f of x plus the limit as h goes to 0 of f of x plus h minus f of x. That's the derivative of f. We assumed that f was differentiable. And so we get this c f prime of x. Okay. So let's do an example with this rule. Just do it over here. Let's let k of x equals 9x to the 4th. Well, then if I take the derivative, k of x, and I take the derivative of 9x to the 4th, let's apply each of those rules. So the derivative of k of x is just k prime of x. First, the constant can slip out front. And we know how to take the derivative of x to the 4th with our power rules. So that's 4 comes down. So I've got 9 times this derivative, 4 x to the 3rd. And of course, I can simplify this to 36x cubed. And so with this new rule, I can now take the power rule and combine it with this constant rule and have any power function with a coefficient I can figure out the derivative to, right? And then we put that together with the sum and difference rule and we get polynomials. So let's finish up with a couple of examples of that. So first, let's write all of our rules. We have, let's let f and g be differentiable and c be a constant. The derivative of a constant, oops, that was supposed to be c, of a constant is equal to 0. The derivative of the sum or difference of two differentiable functions is just the sum or difference of their derivatives. And, oh, the power rule, of course. Not doing this in the same order we did. Oh, I should say n is a positive integer. It is n x to the n minus 1. And then finally, the derivative of a constant times a function, a differentiable function, is just that constant times the derivative. So there's our set of rules right now. And let's show that we can take these and do any polynomial. So let's let f of x equal 10x to the 6th minus 3x cubed plus 7. Okay. Then f prime, we want the derivative right? So first, I apply this sum. It's the sum and difference rule. So I'm using the sum part of this rule, which means that I can split this up into 3 separate derivatives. Oops, that's a minus. Okay, that's the sum rule for derivatives. Now, looking at this first one, I've got a constant times a function. The constant, using this constant multiplier rule, the constant can slip out front. And the same thing applies here. The constant slips out front. And then the last one we have, the derivative of a constant is 0. So we get a 0 there. Okay. Now I'm going to apply my power rule to this in this parentheses. So x to the 6th becomes that exponent comes down front. The exponent left behind is lowered by 1. Same thing happens here. The 0 we don't need to worry about. And now I simply multiply these constants together. So I get 60 x to the 5th minus 9x squared. And this is f prime of x. So there it is, polynomials, right? One of the most common functions, ones we see all the time. We can now take their derivatives, and it's really no big deal, right? You can imagine, and you should imagine, that this derivative, what we just did, is what would have happened if we tried to do the limit as h goes to 0 of f of x plus h minus f of x over h, which let's just write this out once. We're not going to do this whole thing, don't worry. This would be 10 x plus h to the 6th minus 3x plus h cubed plus 7 minus 10x to the 6th minus 3x cubed plus 7 all over h, right? Imagine trying to work through this. You have to take that 6th power. You have to expand that into powers of 6. You have to expand the next one into powers of 3 to the 3rd power, and then you have to multiply those constant through, and then you have to find the things that cancel, combine all the like terms, factor out an h. All that stuff has to happen, right? It did happen. We just figured out a way to shortcut it, and at the end of it, we end up with this in just a couple of lines, right? And when you practice these, right, you're probably starting to pick up on, we don't really need to go through all these steps. This is a pretty straightforward idea. If you look at this, the 6 is going to come down, get multiplied by the 10, we'll get our 60, and we'll get x to the 5th. So after just a little bit of practice, you'll be doing this in one line. And so this massive algebra problem becomes this incredibly simple application of these rules. This is still a function that spits out the tangent line to this function at all the points of x, right? In this case, everywhere, because these are defined everywhere, right? So if I want to know the derivative of the original function f of x at, say, x equals 1, f prime of 1, I can now plug straight into this formula, is 60 times 1 to the 5th minus 9 times 1 squared, which is just 60 minus 9, or 51. So the slope of the tangent line to f of x at 1 is 51. If I want it at 10, I got to throw 10 in, right? It'll get a little bit uglier because we got this x to the 5th, but we can still do that pretty quickly, okay? That's it. That's all we need to do now to take derivatives of polynomials. So it's great. These rules worked out about as simply as can be. We're not going to go through the next rule yet, but I want to introduce why we need it. we've got adding and subtracting functions. A nice extension of that might be multiplication. And what we hope is that if I take differentiable functions f and g of x and multiply them together and take their derivative, we get f prime of x, g prime of x. We hope this is true. That would be nice and simple. Let's do one thing to see if that's true or not. Let's let f of x equal x and g of x equal x squared. Then f prime of x is equal to 1 and g prime of x is equal to 2x. That means that the derivative of f of x times g of x is equal to f prime of x times g prime of x, which is equal to 1 times 2x is equal to 2x. That would be simple. However, if f of x is equal to g of x, then f of x times g of x is x times x squared, x squared, which is x cubed. The derivative of f of x times g of x should then be the derivative of x cubed, which we know from the power rule is 3x squared. 2x and 3x squared are not the same thing. Something's wrong. And what's wrong is our assumption. The derivative doesn't work as simply for multiplication. So that hope is dashed. It's not going to work that simply. And I bring this up right now because once we see how easy these first rules are, it is common to assume, oh, I can just start kind of like derivatives just work the nice way you want them to. And we're going to see an example in the next video where it doesn't. When we multiply, when we have a product of functions, the derivative is much more complicated than just the product of the derivatives, right? But we'll see that next time. That's it for now. For now, we've got these 5 rules. That sum and difference rule I've written as 1, which gives us a huge, we can now do polynomials, which is huge. Okay, that's it. Thanks, everybody. I will see you next time.